Hello, welcome to Regular Achievers Educational Limited, presenting Royal Tutors, your trusted support for brain-friendly, high-impact learning. Today, we'll be looking at the Paper 1 AQA GCSE Physics Overview. If you remember quite very well from our last class, we look at one of the topic from the Paper 1 called energy. So today, we are moving forward to the next topic called electricity. At the end of this session as well, we'll be treating some past questions in line with that topic, electricity. So please pay attention. Introduction to electricity. This topic explores the fundamental principles of electricity, including electric circuits, resistance, current, and voltage relationships, domestic electrical safety, the national grid, and static electricity. Understanding this concept is essential for applying physics in real-life scenarios and exams. Here are some of the circuit symbols that are very much essential for you to know. In your GCSE exam, you can have questions in this manner in which some of these symbols will be given to you and you will be required to identify them. So it's important to be able to identify each of them even right from this session. If you are given any of these particular shape here, this particular circuit here, you should be able to identify them by their name. Electric current and charge. Electric current is the rate of flow of electric charge in a circuit. And for current to flow, the circuit must be complete, or we call it, it must be closed loop. And there must be a source of potential difference like a battery for a current to flow. And there's key equation you need to take note of when you're talking about electric current. We have Q equals to IT. The Q there represents charge, the I there represents current, and the T there represents time. And you need to also identify them based on their unit. The unit for current is amperes, the unit for charge is coulombs, and the unit for time is seconds. In any closed loop, the current remains constant throughout. This means the amount of charge entering one part of the loop is the same as the charge leaving it. Potential difference and resistance. Under this, we'll look at voltage, current, and resistance relationship. Potential difference, or we call it voltage, is the energy that is transferred per unit charge. And resistance is how much a component opposes the flow of current. And the relationship we have between the three of them, voltage, current, and resistance, can be seen in the equation V equals to IR. The V there stands for the potential difference, the I represents the current, and the R represents the resistance. And you need to take note of the fact that the voltage is measured in volts, while resistance is measured in ohms. Note, a higher resistance means a lower current for the same voltage. Conversely, increasing the voltage increases the current if resistance remains unchanged. Resistance and its behavior. So what are those things that affect resistance? Number one is the ohmic conductors. Number two, if you have a constant resistance. And number three, if it follows Ohm's law, which means that current is directly proportional to voltage. And also the last one there, if the graph is straight line through the origin. Non-ohmic component is another factor. In the case of the filament lamp, resistance increases with temperature. In the case of the diode, current only flows in one direction and blocks reverse flow. In the case of thermistors, hotter temperature is equivalent to lower resistance. And when we are talking about the LDRs, talking about the light-dependent resistors, more light is equivalent to lower resistance. Resistance changes due to increased energy in electrons, causing more collisions with atoms in the conductor. Series circuit. In a series circuit, you need to take note of all this information. All components are connected in a single loop. So current is the same through all components. And the total potential difference is shared between components. So if you are calculating the total resistance in a series, you have how total is going to be the first resistance plus the second resistance to the third resistance, as the case may be. Important implications. If one component fails, the entire circuit will stop working. The more resistor that has been added, the more total resistance increases and the current reduces. Parallel circuit. In a parallel circuit, components are connected across separate branches, and each branch gets the same voltage as the power supply. Current splits between the branches as well, and the total current in the sum of currents in each branches. The key point is to take note of. Adding more components in parallel decreases the total resistance because current has more paths to flow through. This is like the adverse of what happened in series circuits. And then parallel circuits are often used in household because each component can be operated independently. Main electricity in UK. We'll be talking about the alternate current and the direct current. Main electricity in the UK is supplied by the alternating current. It has a voltage of approximately 230 voltage and a frequency of 50 hertz. In some questions, they might not even give it to you. You should know this value. And in AC, current changes direction constantly. However, in direct current, it flows in one direction only, like the current from batteries or solar cells. Alternate current is used in main supply because it's easier to transfer over long distance using transformers, and that is what we see being utilized mainly nowadays compared to the likes of the direct current. Plug wiring and electrical safety. A standard UK plug contains three wires: live wire, neutral wire, and earth wire, and they all have their own component as well. You need to take note that live wire, which is often brown in color, it carries high voltage and can be dangerous even when switch is off. But neutral wire, you see that one is color blue, it completes the circuit and the voltage is close to zero voltage. And the earth wire is often color green or yellow. It's a safety wire that only carries current if there is a fault. It prevents electric shock by grounding the current if casing becomes live. Fuses and circuit breakers cut off current if it exceeds a safe level, preventing fires and shocks. Power and energy transfer. Power is the rate of energy transfer, and the equation you need to take note of under this, we have power equals to voltage times current, and also we can use the formula energy equals to power times time, and at the same time we can also equate it to be energy equals to charge times voltage as well. It can be substituted. It depends on the question you are being given. Appliances like kettles or toasters, they convert electrical energy into thermal or kinetic energy. So power rating on a device tells you how much energy it uses per second. A 2000 watt heater uses more energy than a 1000 one. You need to take note of that. Then the national grid. The national grid links power stations to consumers via a network of cables and transformers. We have what we call the step-up transformer, which increases voltage to reduce current. So in such case, less heat is being lost. Then we have the step-down transformer, which lower voltage before it enters home. Since power equals to voltage times current, increasing voltage means current can be reduced, which reduces energy loss as heat in transmission lines. Static electricity and field. Static electricity builds when insulating materials they are rubbed together, transferring electrons. This is something that most of us do most often when we rub our palms together. When you rub a balloon on a fork loading materials, charges is being transferred. The object that gains electron becomes negatively charged, and the one that loses electron becomes positively charged. So when enough charge builds, sparks can jump through the air, and that's why some cases you want to open the door, then you experience some shock. That is what is happening. Static electricity, because charges has been built up over time. Electric field created by electric charges. That is why we have what we call electric field. And the field line shows the direction a positive charge would move. Stronger charges is equivalent to more field lines. The closer the lines, the stronger the field. This explains the force of attraction or repulsion between charged objects without touching. And that is the non-contact force. That is what we mean by non-contact force as well. In conclusion, this topic provided an overview of how electricity works in circuits, including the relationship between current, voltage, and resistance. We have been able to explore how components behave in series and parallel, the importance of safety in mains electricity, and how energy is transferred in appliances. The role of the national grid and the basics of static electricity and electric fields were also covered. Together, these concepts explain how electric systems function in both physics and everyday life. We're going to continue from here in our next class. However, we're going to be taking a look at some past question that's been set from the exam board AQA for Physics Paper 1 in line with this topic that's been treated, electricity.
All right, so here's the continuation regarding the session. So we're going to be looking at some past questions, like I've said earlier on. So here we have the first question that says that an electrical circuit is shown in the figure below. We can see the circuit rightly drawn there. Then we have a question that says that the current in the circuit is direct current. What is meant by a direct current? When we are saying direct current, what does it mean? A direct current simply means that the current is always in the same direction. It means that directly is always in the same direction. So our answer is going to be this. current that is always in the same direction, that is what we refer to as a direct current. Then the next one says that the equation which links current, potential difference, and resistance is potential difference equals to current times resistance. Okay, so that is just simply put V equals to I times R. That's a calculated potential difference across the battery in the circuit in the figure above. Calculate the potential difference across the battery in the circuit in the figure below. So what you want to do is this. It's very, very simple. You know that the formula you're using is V equals to IR. In the diagram below, you can see that from the diagram below, our current there is 0.4 amperes. Okay, then you also find the total resistance, which should be 20 ohms plus 10 ohms. So to calculate this, you know that your resistance will be 10 plus 20 ohms, which will give you 30 ohms. And already in the question, you have been given the current to be 0.4 amps. Okay, so V equals to I times R. Okay, so simply put, you just have 0.4 multiplied by 30, and you will get the answer, which will give you 12 volts. That is just it, and you have your mark. All right, so let's look at the next question thereafter. The next question there says, the equation which links current, potential difference, and power is power equals to current times potential difference. Calculate the power output of the battery in the figure above, and you are expected to give your answer to one significant figure. Give your answer to one significant figure. Simply put, if you remember during the class, I mentioned that power can also be current multiplied by your potential difference. Okay, I multiplied by V. So in this case already, from that diagram we have for the electric circuit, we know that our current is 0.4, and from what we just got now, our potential difference is going to be 12. So if you multiply 0.4 by 12, then you get your answer to be 5 watts. You get answer to be approximately 5 watts. You know, if you just multiply to give you 4.8, but because they say we should put our answer in one significant figure, then the answer is going to be 5 watts. All right, quickly, let's also try some other question. Hopefully, we can answer 2 questions. At least it gives us an insight into what is expected of us from this particular paper. Okay, here we have another diagram. They say the diagram shows a simple circuit. The diagram shows a simple circuit, and we are asked to calculate the total resistance of the 2 resistors. This is also very simple, just like the one we've just done. To calculate the total resistance of the 2 resistors, that's just 9 plus 6, and that will give you 15. So your answer will be 15 ohms. All right, let's move on to the next question there. So the next question there, what do we have? It's a calculate the reading on the voltmeter. Calculate the reading on the voltmeter. Show clearly how you work out your answer. Show clearly how you work out your answer. Show clearly how you work out your answer. So go back up, calculate the reading on the voltmeter, and you have to show clearly how you work out your answer. It's very simple. It's very simple. So to calculate the voltmeter, you know, we're talking about volts here. So that can be the multiplication of the current by the resistance. So that will be 0.3 multiplied by 15. Is 0.3 multiplied by 15, and then we can get the accurate reading on the voltmeter. So you just do 0.3 multiplied by 15, and that will give you 4.5 volts. That's how to calculate the voltmeter reading. All right, let's move on to the next question. It says that we should draw a ring around the correct answer in the box to complete the sentence. Replacing one of the resistors with a resistor of high value will dash the reading on the meter. It's going to decrease the reading on the meter. It's going to decrease the reading on the meter. And the next question there says the voltmeter in the circuit is replaced with an oscilloscope. Which one of the diagram S, Y, or Z shows the trace that will be seen on the oscilloscope? Write your answer either X, Y, or Z. X, Y, or Z. So for the oscilloscope, the actual diagram that will show the trace is going to be Z. It's going to be Y rather. It's going to be y. Pardon me. It's going to be y. Okay. Then we have the next one. Okay. They ask us, okay, why? Why is it y? Why is it y? Okay. Because let me go back to the question of. Because if you look at y shows a direct current. Y shows a direct current. If you look at the question from the beginning, we said that direct current, they are current that's always in the same direction. Y show a direct current, and that is why it is the answer. That is why we picked Y amidst all that right there. Okay, so let's look at the next question. Oh, we're already in question 3. We're already in question 3. Okay. Let's see if we can answer a few questions from question 3 then. So the diagram shows the information plate on its electric cycle. Electric kettle. The kettle is plugged into AC mains electric supply. Okay, then I say use the information from the plate to answer the following question. What is the frequency of the AC? From the unit of frequency, we know that it's going to be hertz, so that's going to be 50 hertz. Okay, and then the next question says, let's go to the next question. Just a minute. The next question says that what is the power of the electric kettle? The power of the electric kettle from the unit, we can see watt right there. So that will be 2,760 watts. That is going to be your answer for the power of the electric cycle or electric kettle. So it says to boil the water in a kettle, 2,400 coulombs of charge pass through the heating element in 200 seconds. Okay, calculate the current flowing through the heating element and give the unit, choose the unit from the list below. This is quite very simple. To calculate the current flowing through the heating element, all you need to do is to divide 2400, okay, over 200. Okay, and how do we get that? We already know that Q equals to IT. Q equals to I, and since we are looking for I, so that will be I equals to Q over T. And your Q already is 2400 and your T is 200 seconds. So if you divide that, that will give you 12. And the unit for current is amperes. Okay, the unit for current is amperes. So that settles that particular question. There you go. So you just pick your amps and you put your 12. All right. So they say the amount of charge passing through the heating element of an electric kettle depends on the time the kettle is switched on. Okay, we can see the graph right there. We can see the charge in coulombs. And at the same time, we can see the time the kettle is switched on in seconds. They say what pattern links the amount of charge passing through the heating element and the time that the kettle is switched on? What pattern, okay, what patterns link the amount of charge passing through the heating element, okay, and the time of the kettle is switched on? This is very simple. If you look at this graph very well, okay, you can see that it is a linear graph. So that shows that the charge is directly proportional to the time switched on, okay? To the time switched on. That is what we can say from this. The charge is directly proportional to the time switched on, okay? In seconds. The charge is directly proportional to the time switched on in seconds, okay? If you look at it, if you look at the time and you look at the charge, when it has, when we have it at 200 for the charge, 400 for the charge, you can see the time taken. You can see when it is 600 for the charge, you can see the time taken. So what do you see? You see that as the time increases, the charge also increases. So that shows that it is a direct proportional effect that it has on it. So when you have a question like this that says that what pattern links the amount of charge passing through the heating element and the time the kettle switched on, you mentioned that, okay, it's a directly proportional effect. It's a directly proportional effect because as the charge keep increasing, the time, or let me say the duration, also increases. So that means if the kettle is being switched on for a longer period, okay, you understand that the current, or let me say the charges as well, has to actually increase. That is what it connotes. So we're going to stop on this for now. So in our next class, we're going to move on to the next topic we're expected to cover under AQA Physics Paper 1. And I trust that you keep following the session. Thank you so much for following Regular Shivas Educational Limited today. Do well to subscribe for more. Bye.